Ethereum side completely blank. And so this is what it would look like over that chart. And as you play that simulation out, you'll see that over about 6 months, it makes about a 30% ROI. So we don't measure things in APY because I think this is a bit of a DeFi deliberate veil, as to how to calculate things. So we just measure everything based in the cash asset that the user has nominated. And so in this particular case, starting with 123.45 compound, you would actually have improved the value of that position by 0.81 ETH over this simulated time period. And then referring to real-world results, again, on the app, you can explore how different people are currently trading these assets. Here's one from the Celo blockchain, where someone with only $7 in liquidity has already achieved a 62.15% ROI in a fairly short time period, trading USDC versus Celo. And this position has traded hundreds of times. So each one of these pages is 10 results long. So we actually allow the user to go and interrogate the blockchain to see every single trade that they've participated in. And there's 22 pages of this data for this user's specific strategy. And so what I'm trying to point out here is that we've really created a system that's much more aligned with user agency rather than the protocol prescribing a very specific trading strategy that we call liquidity provision. So how does this work? Obviously, the mathematics that describe asymmetric liquidity are slightly different or required a slight transformation compared to the traditional, the canonical concentrated liquidity equations. And again, I refer you back to the stuff that I've already published in Archive to see how these things are derived. The only thing you really have to know here is that A and B are rate parameters, and Y and Z are token quantities in some sense. And so if we are going to allow users to choose any set of rates and supply any amount of tokens, then what is a reasonable range to support? Because eventually, Ethereum is going to run out of memory. And this is a really interesting question to tackle. So for example, if you imagine a user is wanting to trade the Shiba Inu token versus wrapped Bitcoin, which is a totally reasonable thing to do, right? These are both highly liquid, very culturally significant tokens in the cryptocurrency economy. The problem is that Shiba Inu is relatively worthless, and I don't mean that is, that the Shiba Inu is a bad token. I just mean that its per token value compared to wrapped Bitcoin is relatively low. So that subscript 9 refers to the 9 leading zeros here, and the problem is that if someone said, I want to trade 1 Shiba Inu for some amount of wrapped Bitcoin, that's like asking how many Ferraris can I buy with a penny, right? You can't subdivide the Ferrari. And so at this point, we're already exhausting the decimal limit that Bitcoin tolerates. It only has 6 decimal places of precision. But it's actually worse than that because Shiba Inu and wrapped Bitcoin both have their own decimalities. The Shiba Inu token has 18 decimal places of precision, whereas wrapped Bitcoin only has 8. And so what this means is that on a token per token basis, sure, it's got 9 leading zeros, but on a token way basis, it's 19 leading zeros, which is a very, very small number. And appreciate that the user can denominate this trade in any direction. Either they're trying to buy wrapped Bitcoin with Shiba Inu, or they're trying to buy Shiba Inu with wrapped Bitcoin. And so you need to support the inverse operation for every single trade. So on a token per token basis, you end up with something like 2 trillion Shiba Inus per one way of wrapped Bitcoin. These are enormous numbers, right? On a token per token basis, sorry, that's on a token per token basis, it's 2.7 billion, and on a way per way basis, it's 27 quintillion way units of Shiba Inu per wrapped Bitcoin Inu. Let's put that in perspective. These numbers are difficult to fathom. The Burj Khalifa is the tallest tower in the world. I think it's still the tallest tower in the world. And it stands at about 128 meters tall. A carbon atom is 1 angstrom tall, so 10 to the minus 10 meters. And so this means that we can, if you were to stack carbon atoms on top of each other, you would end up with a tower of carbon atoms about 8.2 trillion carbon atoms tall before you reach the top of the Burj Khalifa. So let's put that to the side. Now let's consider the height of Bitcoin in Shiba Inu. Like, which tower is taller, and by how much? It is roughly 3.3 million times higher, meaning the Shiba Inu unit used to measure Bitcoin is 3.3 million times smaller compared to a carbon atom versus the Burj Khalifa. These are ridiculous numbers. And we somehow need to process these things on a smart contract using a blockchain that can be roughly approximated to be a fancy like graphing calculator. So the question is like, what is a reasonable range to support? It's like, choose a number. Like, there are instances like this one where we already have extremely large and extremely small numbers to support. So how do you create a protocol that can allow users that level of agency that we don't put limitations on the tokens that they're trying to trade with? And the way to do it is to use a scaling factor. I'm going to try and skip over this because I've only got 2 minutes left in the presentation. But essentially, we use price parameters that are scaled up by a factor of 2 to the 48. And this means that we end up with a slightly different invariant function. And if we were to take some of the price data that we've just seen on the last 2 slides, these are the kind of numbers that we would end up with. Now, the numbers that we actually store in the smart contract are the square roots of those numbers. So there's already a certain level of compression there. But after we've compressed it via the square root, which is fine because that's the way that the swap equations expect the price to be quoted anyway, we undergo a second level of compression, where basically we only select the first 48 significant bits, and then anything after that just becomes an exponent value. And so by compressing it this way into a mantissa exponent pair, we can actually support an extremely wide range of different price values, albeit meaning that the difference between prices might follow something like a step function, which is okay. Okay. So this, on this slide, all I'm doing is showing how this compression process works, comparing it to, let's say, the maker's imagined infinite precision value compared to what we would actually end up with on the blockchain. What this means is that we can actually fit all of this data into only 3 slots, which is why Carbon DeFi is now the most gas-efficient DEX anywhere, right? It has very, very few things that it needs to read and write from, and so all of this complication of where are the bidding prices and where are the asking prices is actually represented in an extremely concise manner. There are parts of this that do introduce error, and so it's really important that we very closely analyze how the makers or the users' intentions are eroded when it gets transformed to the blockchain, and then how that error is compounded by someone trading against it. But I'm happy to report, even in these cases of extreme stress, right, when we're trading things like wrapped Bitcoin versus Shiba Inu, right, remember 19 leading zeros. This is more accuracy than your iPhone can handle. We're still getting about 60 parts per million relative error in one direction, and in the other direction we're getting something like 2.48 parts per quadrillion relative to the maker's imagined infinite precision situation. And if we compare it to what the contract actually has, it's about 26 parts per octillion. If you'd like to see all of these proofs, I have written about it at length, and you can find it on the website blog, and this QR code will take you there. But that's our product, and then we've worked really hard to make sure that it's both secure and represents the user's intentions really well. If you would like to reach me, you can do so at any of these sources. And I am very grateful to have had your attention, and I'm happy to accept maybe 1 or 2 questions. I apologize for going over time.
We were very lucky to get this presentation. Thank you. Unfortunately, we do not have time for questions, but we can meet